Okay, let me share my screen. Can anyone confirm if the slides are visible?
Yes, sir.
Thank you. So we were looking at hash functions, and we finished the probabilistic stuff. And I gave you a general method for the construction of iterated hash functions. In the last class, I also mentioned that there were three kind of problems that we were looking at. Okay, and the important one was the collision resistant, hash functions. So normally we look for collision resistant hash functions. That will imply pre-image resistant hash function and second pre-image resistant hash function under certain assumptions. And so we talked about this iterated hash function general method. Okay, so x double bar y is the concatenation of x and y. The length of string x is denoted by this kind of mod of x. Then we have these compress functions. Okay, and then we basically from the compress function we construct the iterated hash function using three steps: pre-processing step, then processing step, which was kind of compression. You're compressing the strings, and then we have the output transformation, which is used or not used depending upon the the scenario. Anyway, so this is all about the then we started this Markov-Damgard construction method. This is an important method, and what we do here actually, we look at a complex function which is sort of so m plus t input bits are basically converted into m output bits. So this is something very important. And then so when we assume that this is a collision resistant function, so from this collision resistant function we construct collision resistant hash function. Okay, so 1 minute. So hash takes infinite string hash takes finite string of length at least m plus t plus 1 and creates a message digest of uh, bit string of length m. Okay, so now I am going to consider two cases here actually. First of all them is when t is greater than or equal to 2, and the other case will be when t is equal to 1. So case 1 is when t is greater than or equal to 2. So what is the algorithm? Okay, so in this case we treat x in x as a bit string. Okay, and suppose the size of x is n, which is at least m plus t plus 1. Remember t is greater than or equal to 2 here. Okay, then we can take x to be x1 concatenation x2 concatenation and so on concatenation xk, where size of each of these x1 size of x2 and so on size of xk minus 1 is t minus 1. Okay, and the last one x of t minus 1 minus d, sorry, and the last one is xk, size is t minus 1 minus d, where d lies between 0 and t minus 2. Okay, so this will reflect this will impose a condition on k, that k should be smallest integer n divided by t minus 1. Okay, because you see d, when d is 0 this will be t minus 1 anyway, right? And so this is the case. Now we define our function hx as per the following algorithm. We call it as algo 5.6 as per the textbook. Okay, and what is this algorithm is here. So basically, this is a compress function, as you know, from m plus c to m bits. Fine. N is the size of x is n, and k is this quantity, d is this quantity. For this, then there is a for loop, you know, and now we are actually see padding yk. So what is happening if we denote y of x as y1 concatenation y2 concatenation yk. So can you see my screen or not? Can you see my screen?
Yes, sir.
Okay, good. I think there was some problem in the WebEx, you know, so I'm sorry about it, you know, there's some issue. Okay, so as I was mentioned, this Markle demarked construction. So we have this, you know, yk. So each yk is paired by d zeros. So with xk, you know, so the d zeros, and you know, yk plus 1 should be paired on the left with zeros. You know, so yk plus 1 is, you know, the binary representation of d, right? So basically it is paired with on the left with 0, so that yk plus 1 side is also t minus 1. Each basically yi has size t minus 1. Okay, this is what. Then actually we hash sort of x by first constructing yx. Okay, and then processing the blocks y1 y2 yk plus 1 in a particular fashion. So yk plus 1 is defined in such a fashion, is defined in such a way that the mapping x going to yx is injective. Okay, so this is our algorithm, and then we are finally compressing it and returning this hx. You know, so I think now we can talk about the security of this construction. So essentially, what does that mean? That means you know, 1 minute. Let me check. Okay, so okay, so basically I have a main result about the main theorem. Now I can just mention. Sorry, there are a couple of issues anyway. So the main result is basically, suppose we have the complex function. from 0, 1 m plus t to 0, 1 m. So m plus t bits are input and m bits are output is a collision resistant function. And we are assuming t is greater than or equal to 2. Then the function h from I is equal to m plus t plus 1 to infinity 0, 1 raised to power I going to 0, 1 raised to power m. Okay. As constructed in algorithm 5.6 is a collision resistant function. So as long as the compress function is collision resistant, the hash function that we have constructed using compress function is collision resistant, So compress function, why we call it as a compress function? Because it is compressing the bits, m plus t bits into m bits, okay? Anyway, so let me give a proof of this fact that suppose we can find x and not equal to x prime such that hx is equal to hx prime. That means there is a collision, right? Now we will show how we can find a collision for the compress function in polynomial time. Okay, so denote yx as y1 concatenation y2 concatenation yk plus 1 and yx prime is equal to y1 prime concatenation y2 prime concatenation y prime l plus 1. Okay, now x and x primes are padded with d and d prime zeros respectively. X and x prime are padded with d and d prime zeros. Okay, so x is not equal to x prime and we have yx is this, yx prime is this. Now we denote the g values computed in the algorithm. So in algorithm we are computing these g's, right? These g values we are computing, right? You can see that these are the compressions, so which are finally giving us hx. So suppose g values computed are g1 g2 up to gk plus 1 and g1 prime, g2 prime, gl plus 1 prime respectively. Now there are a couple of cases. Case 1, when size of x is not congruent to size of x prime mod t minus 1. Okay, here d is not equal to d prime and yk plus 1 is not equal to y prime l plus 1. Okay, then we have compress function gk 1 yk plus 1 is equal to, you remember this is we are computing in the here this thing is we are computing going into zi plus 1, right? So that is what is compress of zi plus 1, right? So it's compress of gi 1 yi plus 1. So compress of gk 1 yk plus 1 will be gk plus 1 is equal to hx is equal to hx prime because that is given to us is equal to g prime l plus 1, which is same thing as by the algorithm compress of g prime l 1 y prime l plus 1. So this means this is a collision for compress. So we got collision for the compress function. Since yk plus 1 is not equal to y prime l plus 1. So we have found collision for the compress. As we said, we started with the collision for the h function and then we arrived at the collision for the compress function in polynomial time. Okay. Now the other case, there is another case too. Case 2 is that when size is multiple is congruent to multiple of size of x prime. Okay. Mod of t minus 1. Now there are two possibilities. Case 2a. In this case, we say that size is same thing as x prime. This implies that k is equal to L and yk plus 1 is equal to y prime k plus 1. In this case, again we look at the compress function in the algorithm. Compress gk 1 yk plus 1 is equal to gk plus 1 is equal to hx is equal to hx prime, because this is given, is equal to g prime k plus 1 is equal to compress of gk prime 1 y prime k plus 1. Okay, so we have found a collision. So basically we have found a collision if gk is not equal to gk prime, then we found collision for the compress function. Okay, so we assume gk is equal to gk prime. So of course, obviously in this case we have found a collision. Suppose gk is equal to gk prime. In that case, what will happen? Compress of gk minus 1 1 yk is equal to gk is equal to gk prime is equal to compress of gk minus 1 prime 1 yk prime. So either we find a collision for compress for compress function, or what could happen? Gk minus 1 is same thing as gk minus 1 prime and yk is equal to yk prime. If we assume that we do not find a collision, we continue using backwards until we finally obtain that compress of m plus 1 y1 is equal to g1. We are just going backward. g1 prime is equal to compress 0m plus 1 y1 prime. If y1 is not equal to y1 prime, we found a collision for compress. Okay. So we assume that y1 is equal to y1 prime. But then this will imply that yi is equal to yi prime. Okay. Or 1 less than equal to I less than equal to k plus 1. And this will imply that yx is equal to yx prime. Okay. And this implies that x is equal to x prime, which is a contradiction. Because we assume that x is not equal to x prime initially, right? Since x going to yx is injective function. This is also another thing that we have assumed. Okay. Second case 2b was when this is not equal to this. Then without loss of generality, we can assume that size of x prime is greater than size of x. So L is greater than K. Similar to case 2a, actually, assuming we find no collision for compress, we eventually reach the situation where we have that compress of 0m plus 1 y1 is equal to g1 is equal to g prime l minus k plus 1 equal to compress g prime l minus k 1 y prime l minus k plus 1. Okay. So, but m plus first bit of z 0m plus 1 concatenation y1 is 0 and m plus first bit of g prime l minus 1 1 y prime l minus k plus 1 is 1. Therefore, we find a collision because they are different. Okay, for the complex function. So basically, I just want to summarize that if the complex function is a collision resistant function, then the compress function is then the hash function is a collision resistant function. So this is the case. So I think similarly we can do for t is equal to 1. So I should mention briefly what happens for t is equal to 1 case, because here we assumed that t is greater than or equal to 2. Okay, we assume t is greater than or equal to 2. In case t is equal to 1, we it depends on a special function. The construction depends on a special function f. So suppose size of x is n, which is at least m plus 2. And suppose f is a function which is 0 and f1 is 0 1. So hx is constructed in algo 5.7. So I think let me see what is algorithm 5.7. Here it is. So what you do, compress function is, because t is equal to 1 here, this is m plus 1 bits are going into m bits, n is the length of the size of x. And you see we have the concatenation and we are adding this 1 1 in the beginning of this function. So function f, as I mentioned, so f0 is equal to 0 and f1 is equal to 0 1. Now encoding s going to y is satisfying two properties here. Okay. I mean, the first, this is the injective function. Okay. First property, this is the injective function. X going to yx is an injective function. Okay. And second, there does not exist two strings x not equal to x prime and z such that y of x is equal to z concatenation of y of x prime. That means no encoding is a postfix of another coding. Okay. So since yx begins with 1 1 here, there does not exist two consecutive ones in the remainder of the string. Okay. So then we have a theorem 5.7, which is for this special construction t is equal to 1. The theorem is, suppose we have the compress function taking m plus 1 bits to m bits, okay, is a collision resistant function. Then h from union I is equal to m plus 2 to infinity 0 1 I to 0 1 m as constructed in algorithm 5.7 is a collision resistant. hash function. Okay. So the proof is simple. So I'm just including it here. Suppose we can find x not equal to x prime such that hx is equal to hx prime. Okay. So we are saying that we have found a collision, right? X is not equal to x prime. Okay. So in that case, what will happen? If we denote yx is equal to y1, y2, yk, and yx prime is equal to y1 prime, y2 prime, yl prime. Okay. In this algorithm, you see this is y. We are denoting concatenation of y1 to yk. Now there are two cases possible, so we are just doing one by one. Okay. Case here. Okay. So case one, when k is equal to L. As in theorem 5.6, either we find a collision for compress or we obtain y is equal to y prime. We find collision for compress or y is equal to y prime, which implies that x equal to x prime, a contradiction, right? And case 2, when k is not equal to L, without loss of generality, assume L is equal to k. Assume we find no collision. For compress, we have yk is equal to yl prime, yk minus 1 is equal to y prime L minus 1, so on y1 is equal to y prime L minus k plus 1. This contradicts the postfix free property, right? Because things are same here. This implies that H is a collision resistant. Okay. So I think now I can give you some examples. This was all some basic theory about the construction. Some examples are important because that is what I think you may want to look at. Some examples of iterated hash functions. They use this approach MD4, Message Digest 4. It was given by Lewis in 1990. Then Message Digest 5 was again given by Lewis in 1992. SHA stands for hash algorithm. Okay, so this is a standard in NIST in 1993. This is published in FIPS 180. Later on, this was also known as SHA0 because then more versions of SHA were found, like SHA1 with slight modification. In 1995. Okay, so that is SHA1. So collision of these compressed functions were found in for MD4 and MD5. Collision was found. Collision were actually discovered in 1990. discovered in mid-90s. Okay, so then these algorithms were no longer secure. Okay, so secure hash algorithm. Okay, SHA stands for secure hash algorithm. Okay, in 1998, weakness led to fine collision in 2 raised power 61 steps in SHA 0. 2 raised power 61 steps, collision was found. In 2004, again SHA 0, collision was found. 2004, MD5, message digest 5, collision was found. All these, Then 2017, in SHA 1, first collision was found. Okay. Then a new algorithm SHA 2 was introduced actually, and it has 4 hash functions. This was in 2004 actually, yes. 2004. So one was SHA 224, SHA 256. These are 4 hash functions. SHA 384 and SHA 512. Okay. So these are nothing but sizes of the MD, message digest. All these are size of the message digest. Finally, in 2015, 2015, a new algorithm SHA3 was discovered. I mean, this was based on a new construction known as based on sponge construction. Okay, so it was 5th standard in 2015. So this is pretty nice algorithm. So what are the operations used in SHA1? I think I can show you. Yeah. So these are the operations used in SHA1 are bitwise AND. Okay. So the compression function I should mention here maps 160 plus 512 is equal to 672 bits to 160 bits. And these are the operations bitwise AND, OR, exclusive OR, bitwise complement, integer addition modulo 2 is equal to 32, and rotation. Circle left shift of x by s positions. Okay. These are the actually I'm not giving you too many details of SHA1, but it's just general idea, how it worked. Okay, so maybe now I should give you some idea about SHA3, how SHA3 works, So that is an important one. So all these MD4, MD5, SHA1, SHA2, SHA3 produce message digests, So basically message digests are outputs of hash functions, right? So I can mention about sponge construction. sponge construction. So FHA3 is based on this construction. So secure hash algorithm. Okay. So we use functions of some kind here, which takes B input to B outputs, and these are bijective functions. Means one-to-one and on-to functions. Okay. B is known as width. Okay. B can be written as R plus C. We decompose B bits into two sections, R bits and C bits. R is known as bit rate. So basically we are using R bits at a time, kind of processing it. Okay. So R is also known as efficiency of the sponge function. Okay. And C is known as capacity. This affects the security. Okay. A security level against a certain kind of collision attack is intended to be roughly 2 raised to power C by 2. Okay. Let me show you the figure of the sponge function. This is a sponge function. What it does, input is, message M. Okay. So bit string of arbitrary length is going here, and this is padded, so the length is a multiple of 4. Sorry, length is a multiple of R. Okay. So then this is split it into two sections, R bits and C bits. You can see that here. And initial value is 0. So this is known as state. The initial state is a bit string of length B. This is length B. Okay. This is length B. Okay. All 0. Okay. So then there are two phases here. One is known as absorbing phase of the sponge function. This is the absorbing phase and the squeezing phase. Okay. So absorbing phase, what happens? Basically, F is applied. This function is applied here to these R bits, and then with the padded things from F, M, this is applied in each state. The application of F updates the states, of the function. Okay, so let me give you more details about this. There are two stages. Final output is this. Okay, L bits are output. Okay, so let me show you. Suppose the padded message is M is equal to M1, M2, concatenation MK. Now each MI is binary string of length R. 1 less than equal to I less than equal to K. Okay. Define X0 R bits. Okay, these are 0, and Y0 C bits, which are 0. Now you can see that this picture R 0 here, C0, all these bits are 0 here. Okay. Then we are computing the functions. So we are computing here functions, right? So how these functions are computed here, we can explain. F M1 XOR with M1 bits and concatenate with Y0 is our X1 concatenation Y1. Next function X1 M2 concatenation Y1 is equal to X2 Y2, and so on. function of x k minus 1 mk configuration yk minus 1 is equal to xk configuration yk. So xi's are bits of length r and yi's are bits of length c. Okay. So this is how this function is sponge function is working as absorbing phase of the message, right? Now, so bit string xk yk is the output. You can see that this output here is xk yk. This is the bit string that is output here. Okay, of the absorbing phase. Xk yk is the output here. Okay. Now there are two cases. If L is less than or equal to R, L is the output bits desired, how many bits you want. If L is less than or equal to R, then message digits Z consists of, you see in this picture, this is the Z MD. Message digits Z consists of first L bits of xk, right? And if L is greater than R, more F is applied. Actually, how it is applied, let me explain. So we apply F to the current state. So number of desired bits are more than R. In that case, we are doing this. Current state, which is R plus B bits long. Okay. Take first R output bits as another output block. R output bits as another output block. And this is repeated unless we have total of more than L bits. Okay. Finally, we truncate the concatenation of the output. Just truncate. To L bits, so that the desired L bits are obtained. Okay. So basically, that is all about sponge construction. We can talk about the security of this sponge construction and so on. But I think now maybe we can start the public key cryptography. Of course, there is. I can talk about MSCs also, but we'll see. At some point of time, we'll talk about it. So first, we will cover some public key cryptography now, especially the two chapters next. So you know RSA crypto system, right? Which is a very common one. So we have heard about it in your discrete math class. So we are going to look at some details, more details about RSA crypto system and some of the attacks possible. Similarly, on the discrete log problem, what are the possibilities? So that's all for today. I think I'm going to give you the project details, how the project has to be executed. I will announce it on WhatsApp and I will let you know. Okay. That's also next class will be online, and after that there will be online and offline as well. So okay. In fact, I should mention this. This is the security levels for SHA3. So they are still in use basically SHA-3, Anyway, thank you very much. So let me stop.